I didn't do it.
The wonders of Zoom.
Yeah,
So
sorry about that.
everybody, good to see you this morning, and a special privilege for me and a pleasure to introduce Benoit Taisne. Benoit was studying in Paris. He started there about the turn of the millennium, I believe, and at the École Normale Supérieure, and then in his master degree, he did there as well as in the Institut Physique des Globes of Paris, where he went on to his PhD. His PhD was focused on dikes, especially using gelatin tanks experiment for analog. And I think this is still going on. I know that this is still going on, but this is not the topic of today. A few more words about Benoit before I let him talk. He is an associate professor at Singapore at the Nanyang Technological University. And also he's the associate chair of research and teaching. And I had the privilege to meet him when he was little in Paris. And as he grows nice in Singapore, we run together a project in Troodos, ophiolite. But today is going to talk about related but very different aspect of his research. And you had the time to watch the title. So Benoit, without further ado, you have the mic.
Thanks, Amos, for the introductions, and thanks, Uri, for the opportunity to present my research today at your department. As Amos mentions, I started off looking at how magma migrates through the crust, and then I kind of got frustrated by the theory and the experiments, and I moved into understanding the monitoring data. And ultimately, when the volcano goes boom, what is the impact on these eruptions on the populations? And turns out that there's still a knowledge gap in understanding from the distance, understanding the dynamic of an eruption. And in this presentation today, I hope to convey that there's a lot of things we can do remotely to mitigate the impact of volcanic eruptions. So this is, as usual, full disclaimer. All the cool stuff is coming from my team. Any mistake that you might see are coming from me. And this research is supported by the Center of Geohazard Observations, which is embedded in the Research Institute and helping us to install and maintain instruments. So I'd like to start up with a little story. And this story will take us to Indonesia, a bit far from you, closer to me. Let's say we are on a boat sailing off the coast of Indonesia. It's 6 a.m. in August 1883, and boom, we can hear the loudest sound ever recorded on Earth. It was the collapse of Krakatoa volcano that triggered a tsunami and one of the highest death toll in volcanic history. So the sound, the one we can hear, was heard more than 3,000 kilometers away. And the sound was so loud, so energetic that we had frequencies leaking down into the low frequency, into the infrasound. And I will make sure we're on the same page in a minute. But this atmospheric disturbance were recorded all the way across Europe. And we have here two little dip in the pressure recorded in St. Petersburg, Brussels, Paris. And those are the pressure waves associated with the eruptions of Krakatoa. So August 83 is really the birth of infrasound, of remote monitoring of explosive events. So it's quite an honor to be working on infrasound in this region. One of the challenges we're having, though, is to identify the source. So now I'm taking you to a typical seminar setting. Okay, we have a room, we have a speaker, and what we want to do is listen to the speaker most of the time. However, outside in the corridor, we have people drinking coffee, and within the room, we have people that are not always listening, they are whispering. Hopefully not too many of them are snoring, and you are here trying to concentrate, trying to focus your attentions on the speaker, which is the source of the sound you want to listen. I know this is an unusual setting for the last year. This is a kind of seminar room, is busy. So if we translate that into lockdown periods, you have to listen to someone speaking to a computer. You might have a cat, a dog, chips, constructions. Anyway, you want to filter external sounds and focus your attentions on the signal of interest. And that might sound a bit, disconnected, but you will see that one of the challenge we have is actually this, concentrating on the signal of interest. Humans are great mammals. They have a lot of functionalities. However, what they can see in the electromagnetic spectrum is very, very narrow. And what they can hear in sound frequency is also very narrow. So the sound that we can hear are at frequencies below 20 and 20 kilohertz. The ultrasound, which is much higher frequencies, will be above the 20 kilohertz. And finally, the signal of interest for today, infrasound, will be anything below 20 hertz. Those infrasounds have been of interest for many years, and the militaries have been developing techniques to track boats or aircraft all the way back to the 1880s. What they were doing is extend the two sensors we have, our ears. They will extend them to be sensitive to lower frequencies, and then by turning the head, they would stop whenever they can hear the sound in both ears at the same time. When that was the case, they would be facing the direction of the source of the sound, the direction of the aircraft or the directions of the boat. The technology evolved now, but the idea is the same. We want, using instruments, we want to locate the source of the infrasound. The data that I'll be using use so-called array geometry. So it's not a single sensors, it's multiple sensors put in a different geometry. And in a nutshell, what we will do is do some cross correlations between those different channels to align them. And depending on the delay between those different channels, we defined a back azimuth and an apparent velocity, which is related to the elevation angle, if you wish. Those arrays are deployed all around the globe as part of the international monitoring system to control and make sure that nobody is testing chemical, developing new chemical or nuclear bombs. However, a lot of infrasound are actually generated by a wide range of natural sources, from bolides entering the atmosphere, from tsunamis or surfs, volcanoes, and hurricane. For today, the interest will be on volcanoes, but toward the end of the talk, I will be playing you some infrasounds that I would speed up the infrasound so we can hear them of different natural phenomena. So stay tuned, that will come toward the end of the talk. Sounds good. We have sounds. Now, how do we record them? The sound that is emitted somewhere will propagate through the atmosphere, which is quite a complex and ever-changing medium. So one of the big challenge for infrasound compared to seismology, for those of you who are more familiar with seismology, is that the medium is ever-changing. And in order to extract information from the source, we will have to take care of this. If I had to compare that with you working with friends in a storm or a lot of high winds, it will be easier for you to talk to someone that is downwind compared to you than to talk to someone that is upwind compared to you. Similarly, for the infrasound, we can generate a map like this based on weather conditions, and the color here is telling you the minimum acoustic pressure needed at this location in order to be recorded by at least one stations. The stations are represented by those white triangles. The red triangles corresponds to different volcanic areas of interest. So if we do that through times and we picked a region of interest for Sumatra or for the Philippines, that would be 9 years of minimum acoustic pressure needed in order to be recorded by at least one station. So now if you look where is Singapore, it's here. We did install a station, an array here in Singapore. So if you look at where the spotlight is, you will see the difference. So now I will add the station in Singapore, and you see that all of the students, we have a large area of blue, of low minimum acoustic pressure needed in order to be recorded. The impact is dramatic for Sumatra, which is the closest from Singapore, a bit less dramatic for the Philippines. But in both cases, we improved our ability to detect an event. Why? Because we lowered the minimum acoustic pressure needed in order to be recorded some fraction of the time. And that's one way to quantify it. We defined the improvement factor, which is the ratio between the minimum acoustic pressure needed using the international monitoring system alone, divided by the minimum acoustic pressure needed by combining the IMS with Singapore. And with Sumatra, how we can read this diagram is that 40% of the time we increase by a factor of at least 3. The acoustic pressure needed is 3 times lower 40% of the time when we add this station in Singapore. For the Philippines, it's farther away. It's a bit less impressive, but still 20% of the time we improve by a factor of 20%, 1.2. And so that's the rationale for why it is important to have a station in Singapore. So now we did that and say, okay, well, where am I going to install a station in such a small land area? Infrasounds are sensitive to ambient noise, so in the middle of the city is a bit challenging. We narrowed down on a natural reserve, one of the national park in Singapore, which is MacRitchie Reservoir, and we have installed 5 sensors. Those 5 sensors together corresponds to the station in Singapore, to an array of infrasound sensor in Singapore. To give you a flavor of the field conditions in Singapore, it's on the equator. There is rainforest everywhere. Those sites are off the beaten tracks, and you need a boat, jump out of the boat to go into the jungle and maintain your instruments. How do we quantify the quality of these stations? This will be done by looking at the frequency content on the x-axis and the acoustic power on the y-axis. I will draw your attention on two regions. In the 0.1 to 0.3 hertz, that's the band of the microbarometer, which is due to the interaction between the atmosphere and the ocean that have nonlinear interactions and produce this ever-present noise or energy in the infrasound called the microbarometer. The fact that we can see it is a good sign because this is a semi-permanent source of infrasound. So that was the first good news. The less good news is that above 8 hertz, this peak here is due to anthropogenic noise. So anything above 8 Earth, it will be really hard to extract these informations from the data. The good news is volcanic infrasound, especially remotely, are below 1 Earth. You can see that we have 5 sensors, and I told you earlier the goal of combining those sensors is to track the back azimuth, track the source of the infrasound. And that's done here. We have 10 days of data or so. The color corresponds to the dominant frequency of the signal that is coherent across the 5 sensors. And here we have the directions, the back azimuth of the signal. The macrobarometer is gently oscillating south of the stations, and you can see that this 10.8 Hertz peak from the anthropogenic noise is really constant in back azimuth. And we had an undergrad student running a project, and she located the source of this fixed source of infrasound within the business district. So if we plot this on a map, that's what it will look like. We have the stations in Singapore. This macrobarometer is mainly coming from the south, which kind of overlay with the directions of the volcanoes in Sumatra. So that might be not so good news, because we want to be able to detect those volcanoes. So if I look at the percent of the time I have strong macrobarometer in a given direction, I can see that overall over a year I have 4% of the time I have a strong macrobarometer covering Sumatra here. Another way to look at this, 4% of the time, if there is an eruption, it will be challenging to detect it. Or these eruptions will have to be extremely energetic to be above the macrobarometer. If we look across a month, we'll see that depending on the seasons, we have a different monsoon system. And in April and May, it will be much challenging to clearly detect an eruption from Sumatra compared to Northern Hemisphere summer month. So now it's great. We have quantified the noise at the stations. We have estimated our ability to detect an event. Now let's look into actually volcanic events. For those who are not familiar with volcanic events, just in a nutshell, we will use, or I will be using the volcanic explosivity index, which is a scale from 0 to 8, 0 being small eruptions, all the way to 8, which are gigantic eruptions with global impact. Each of those VIs are associated with ash volcanic plumes that put ash into the atmosphere, and this is a concern for aviation. So you have here a typical flight level. When you were traveling and when you would be traveling, usually you are following flight level 350, 10 to 11 kilometers. And you can see that a VI3 and above will potentially impact this flight level. How frequent are those VI3 and 4? If we look into all the volcanoes that we looked at in Southeast Asia, we started with 749 volcanoes. By combining the likelihood of each of those volcanoes to erupt, it turns out that in every 10 years, you are almost certain to have a VI3 and 4. Within 10 years, VI6 and 5, which is Pinatubo scale of eruptions, are above a 10% likelihood. So, it's one of those cases where it's not if, but when. And that's a good argument to say, okay, let's maintain those infrasound and be ready for those big events. How big and how far can I detect? So from this study from Dabrova et al. 2012, they looked at the plume height above the summits, and they identified the distance at which an infrasound station would detect or not the eruptions. So an open circle is a detections leading all the way to a black circle, which is the most distant detections for this eruption. And a red cross is no detection. There's one thing that is important in this plot is all the events are detected by stations located less than 1,600 kilometers away. And that is an important information that I can convey and plot on a map. So now if we look at all those different stations from IMS and from Singapore, you can see two circles, a 1 hour infrasound travel time and a 1,600 kilometers. So any volcanoes within those circles will be detected. It will take time. Infrasound is painfully slow, is the celerity of sound, 340 meters per second. So it will take time, but you will detect those eruptions within 1,600 kilometers. The not so good news is those magenta volcanoes that are further away than the 1,600 kilometers. And those volcanoes are actually the one that are the most likely to produce. The maroon color here corresponds to the potential of more than 45% probability to generate a VI4 in the next 10 years. So part of the research project we have here is to add infrasound stations in these regions to reduce the time needed to identify and characterize one of these events. So the title included impact and mitigations. So I've been talking about volcanoes, volcanic eruptions, but how do they impact the populations? In this diagram from Susanna Jenkins, 2015, we have on the x-axis the distance, on the y-axis the ash thickness, and we can see that the closer we are from the volcano, the thicker the ash. But if we go far away, we still have layers of ash that can still impact the populations, impact the infrastructure, and impact air travel. So how do we, and all those different parts of our daily life are impacted will depend on the amount of ash. So in the same paper from Jenkins et al., they look at different grade of damage, from no damage all the way to beyond economical repair. And you will see that for airports, anything above 0 millimeter, so literally any ash reaching an airport will close the airport. That sounds a bit dramatic. However, if I know the ash is coming my way, in 2 or 3 hours, I can try to make sure all the aircraft that are ready or sub-ready to take off are pushed away, and all the aircraft that will remain on the ground are protected. And that's what I call mitigating the impact. In order to mitigate the impact, I need to know when and where and how much, and that is through modeling. If I know there is an eruption, if I know where this eruption is, if I know the type of eruption, then I can model one phenomena, let's say ashfall, tephra and the model will tell me where and how much and when I will have this impact. I started describing this figure by if we know, if we know, if we know. And that's where the infrasound, and at the end, I will, touch based on other technologies, but that's where infrasound can really help to put the numbers on those if. Why? Because right now, when people are running those scenarios to close airspace or to communicate with people on the ground, they use one operational scenarios, one realizations amongst many. If we simplify what could be an eruptions, if an eruption is from big or small, the eruption itself is, let's say, in red. The operational scenarios could be an underestimations of the eruption. In that case, I underestimate the potential impact of this eruption. On the other hand, I can also overestimate the impact of this eruption. So in both cases, I have limitations. So the questions here I'd like to answer is how to better characterize an eruption remotely, and how can we assimilate new informations, new data as they came to improve our knowledge about this eruption through times. The source of the data we'll be using are from the international modeling system, from local monitoring, as well as research arrays or sensors. And the aim is to reduce the uncertainties on those eruptions parameters, and hence to increase the accuracy of the forecast, and at the bottom of the line to increase our level of confidence in triggering mitigating action. So how does it work? We have a volcano. Infrasounds are generated when the volcano is erupting. So we are not trying to forecast the start of an eruption. We are trying to forecast the impact of an eruption. So the eruption is ongoing. We have ash being spewed into the atmosphere, interaction with the atmosphere, infrasound. Those infrasounds will travel and be detected and recorded at sensors. Based on this signal, we can estimate some acoustic parameters for the source. And from those acoustic parameters, we can estimate some eruptions of the eruption itself. When we have those informations, we plug it back into the modeling of the volcanic impact. So when an eruption is detecting through infrasound, we can estimate the location, the time of the eruption, we can estimate the source amplitude, and finally the plume height from the acoustic power. There's another parameter we can extract, which is the duration of an eruption. I'd like to highlight one project here in one slide. I won't spend too much time on this one. This is the results of the research of an undergrad students here, where he looked at power spectral subtractions of noise to a future signal, trying to improve our ability to detect a signal. So the amount of noise you remove and the amount of time you use to learn the noise, you can improve. This green blob is when we detect an event. You can see that here it's a small green blob, and here is a bigger green blob. We have improved our ability to detect this eruption. And those type of research are a key in the research we're doing, and they will be slowly implemented into the real-time analysis that we are doing right now. Okay, each plug that we can have to improve the detection capability, each future research that can be done, improving anything can be added to the real-time analysis. Okay, when I have a detection, this one is from the Sangyeapi eruption in 2014. It's been detected at multiple arrays. And here you have the amplitude, the acoustic amplitude at the sensor for around 0.1 hertz. Okay, so this is the amplitude recorded at different stations. The x-axis will appear next is actually the distance from the source. Okay, so this is the distance from the source and different stations at which the signal has been recorded. So from the amplitude of stations, we have to estimate the amplitude at the source. And here we have the first layer of uncertainties that is added because we have to model the attenuation between the source and the station. And that's going through the atmosphere. And this attenuation is tied to uncertainties and will change depending on the day. So this is the first source of uncertainties. From this amplitude at the source, I can estimate an acoustic power at the source by basically integrating the signal. Those values are really high, 10 to the 8, but in order to put them into context, I will draw the line for the Beirut explosions last summer that had an acoustic power estimated to 10 to the 8. So this eruption at Semeru was 1 or 2 orders of magnitude higher than this chemical explosion in Beirut. So from this acoustic power, I can extract an exit velocity. How fast do I push something into the atmosphere? And now I start to have a physical sense of what is happening at the volcano. Velocity is meter per seconds. I can visualize something happening at a volcano. Okay, that is the first physical parameter that we'll play with. It's not enough to estimate the plume height. From the exit velocity, I want to have an idea of the mass flux. I'm missing 2 things here. I'm missing the size of the radius of the volcano, the size of the vent of the volcano, and how much mass, how much magma is actually inside the plume. If I use a reasonable range for those 2 parameters, I can finally have the plume height with associated uncertainties. Okay, the dashed lines are 2 different estimates based from ground and satellites, and you can see that from infrasound, more than 5,000 kilometers away, I can still retrieve a useful estimate of the plume height, which is in the range of what has been derived from satellite and from the ground. What are the source of those uncertainties and how can we improve them? I told you that from the exit velocity, we had to estimate the mass flux, and that goes through the radius, which is the green part here, and the mass, which is hidden into Q magma. So if I have no idea from where this eruption is, I can use reasonable distributions for all those radius. Distributions are described at the bottom here. So by inputting all those probability of radius, probability of mass, uncertainties on the acoustic power, I have a distribution of plume height for this eruption. If I know the volcano, I can then have a better knowledge on my radius, and you can see that the range of the distribution is reduced, though the standard deviation is fairly close. This is because here we have a log normal long tail, and here we're using a Gaussian distribution. And the next parameter we would like to improve is the amplitude and the mass, how much mass is in the plume. And those will be really hard to estimate from the distance. So we will have to be honest and being aware of those limitations, but we can provide with associated uncertainties a range of distributions for the plume height, which is already better than this single operational scenario. There's another things we can extract, which is the duration of intense phase of eruption. In this example, published by Corentin Condron in 2015, we have highlighted here this long-lasting phase of intense infrasound that lasted for 2 hours. So for this eruption, we know that it was not just a single boom, but it was intense for 2 hours. And that is critical for the simulations of ash dispersal. Something a bit more extreme, 2 years ago at the eruptions of Anak Krakatau, the child of Krakatau, where we showed that we have a clear signal from remote infrasounds. The azimuth here is the azimuth of Anak Krakatau. We have a little shift in frequency. However, we have this long-lasting signal across multiple days. So these eruptions was injecting ash into the atmospheres for multiple days. So this one was clearly not a single boom, was not even 2 hours, it was over multiple days. And that was published last year by Anna Pertu, which is research assistant in the team. So to summarize a little bit, infrasound, when, where, how big, how long? Yes. Another big plus of infrasound is they don't really care if it's the day or the night compared to satellite. They are cloud-free compared to satellites, and they can travel thousands of kilometers away from the source. Currently, they are used to detect eruptions where and when, and I hope that I convince you that we can also extract information about how long, and this eruption lasted for 2 hours, and how high. For Sangye-Api, we have an estimate using infrasound. We have an estimate of the plume height. There's something else in this figure that I want to point. The little green volcanoes corresponds to the volcanic ash alerts issued by the volcanic ash advisory centers. And what you can see here is the dashed lines. At least three dashed lines came before the first reports. Those dashed lines correspond to the time at which the infrasound reached a station. And even though infrasound is slow, it can still arrive and give us information about an eruption before it is officially reported. And the initial reports were underestimating the height of the plume, which is the same case here for Sangye-Api. The first information came from IO7, less than a couple of hours after the start of the eruption, and the plume height estimates is on the money compared to the first initial reports that underestimated the plume height. So, there is a lot of value in including those data into operational setting. And that's kind of loop back to this framework. Hopefully, I convince you that as an eruptions and crisis developed, we can better characterize the ongoing eruption, and we can assimilate those new informations coming from infrasound. The source of infrasound data, I already mentioned them, but I don't want to oversell the techniques. There is other data available, publicly available. There is weather forecast satellites that are freely available. There's radar data, crowdsourcing using social media. You'd be amazed to know the things that we can extract from social media. And that's a project with another colleague. And that will be another story for another time. So now, hopefully, I convince you that with all of these informations, we can further reduce the uncertainties on our knowledge of the ongoing eruption, hence further increase the accuracy of the forecast, and finally gaining a reasonable level of confidence to tell this person in 2 hours, make sure you are inside. Kids playing at recess outside, make sure you go inside the school. Here, make sure you properly shut down your critical infrastructure. Make sure you don't fly in this area. So with this level of confidence, there's a lot of things that can be done ahead of time to mitigate the impact of the eruption. And that concludes the kind of the main meaty part of the talk. And for those of you who are still awake and stayed with me all the way until now, you'll be rewarded with some nice sound. So that will be a time where you crack up the volume and you enjoy the sound of nature. I mentioned this international modeling system before. This system has been recording a lot of events. The first event I will play is the infrasound associated to the Tohoku Oki earthquake in March 2011. You will hear different type of sound. You can hear them because we speed them up. Okay, infrasound, I told you, and it's true, it's below human hearing. But if you compress it, if you play it faster, you can hear them. And this has been cleaned and tuned by my friend and colleague, Milton Garces. I play it again because if you close your eyes and you don't know where you are, you might be facing a deep sea monster or something. That's the vision I have when I listen to it. Well, so I hope I won't trigger any nightmare for tonight, but I think this sound is fascinating. The next one will be coming from Hawaii, provided by Anna Pertu, and that's the collapse of Pu'uho crater years back. Not the recent one, but a few years back. So this video is interesting. Why? Because you can hear different frequencies. You can hear this click, 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 which has linked to rock falls, pretty high frequencies. And then at the end, you have this deep infrasound, this deep sound. If you have a subwoofer, put it full blast and your body will vibrate. And that's the collapse of the full structure. So a small structure will have higher frequency compared to the big collapse of the lake. We play it one more time, just because we can. The next one, still from Hawaii, it's a degassing event, and again you can look at the different frequency band here, the low frequency, mid frequency, and high frequency, and try to jump between this and the video to appreciate the scale of what is happening and where is the energy. So hopefully you notice that when we have this intermediate range and the low frequency, that's when the action is really going on. The very last sound, and then we'll be opening the floor for questions, is the sound of an eruption from the distance. So we go back to the region. We have the Kelut eruptions in February 2014, and this is recorded in Singapore. So I know it's a bit less sexy, I know it's a bit less amazing, but this red, blurb of energy, it's the expected arrival for Kelut, and from this we could extract information. Most of the research you've been looking at today are from those recent papers. So I think I will leave this slide so you can, snap the QR codes and download the paper, and I will be happy to take any questions. Thank you so much.
Thank you, Benoit. That was great, and especially the end. The sounds at the end were awesome. Questions? You can unmute yourself and fire away.
Benoit, so can you tell us if it's possible using the infrasound technology to also find out about the process, something that you cannot with the alternative sources of information, or you use it mainly for mitigation? Alarm.
If you refer to satellite, for example, there is some information that you won't be able to get from satellites depending on the cloud cover, or it can also be covered by the first phase of a volcanic eruption. So what we would gain from the infrasound is being able to have a mental picture of what's going on, even if it's covered for any kind of view from above. What do we gain from people on the ground? Nothing. If you have people on the ground looking at what's happening and communicating in real time, that is the best. Okay. Though from the ground, I challenge you to tell me if it's 15, 20, or 25 kilometers, because that would be extremely hard. So what we gain from the ground, from satellites, and from those remote data like infrasound is a comprehensive picture. Each will feed its own informations that can be constrained by the other ones. So I'm a big fan of using those different techniques together and not only one.
I have a question, please. First, thank you very much for the fascinating talk.
Thank you.
And very interesting. Is there any option to detect submarine eruptions this way?
So the technology used for submarine eruptions won't be the infrasounds, but we can have acoustic sensors that are underwater. Those are same sensors are used in the international monitoring system, and those are the one you will want to look at to detect the submarine eruption. The infrasound is when we have direct interaction with the atmosphere. So when the submarine eruption became Cestasian or somehow interact with the atmosphere, then yes, we will have infrasound produced.
Thanks.
Benoit, very nice talk in Typhoon Geological Survey. I wanted to know, what about coupling your acoustic infrasound sensors with the seismic stations?
Yep.
Because I suppose you can gain faster information, at least when you talk about locations, if you couple your seismic instrumentation with the infrasound stuff.
No, thanks for the questions. It's excellent point. So I told you infrasound was painfully slow, and you're right, seismic will be much faster. I've been using infrasound for two reasons. The data I'm using are open to the public, which is not always the case for the national seismic networks in the region. That's one answer. If you have access to the regional seismic sensors, the coupling with the solid earth need to be extremely large, and the intensity need to be extremely large in order to be recorded far away. Why? Because the acoustic wave will be much higher frequencies and attenuate much faster. And then if we look into close to the volcano and we have a monitoring system with the sensors on the flank of the volcanoes, then it's golden. That's what you want. But the sheer number of volcanoes in the region imply that they're not all instrumented. Most of those volcanoes will have one instrument, which is likely to be destroyed in the first phase of the eruption. So that's kind of a convoluted answer, but hopefully that answered your question.
No.
No? Okay.
Partly, because what I was thinking is to couple actually. I mean, you did a lot of effort of putting your acoustic infrasound in those places, remote places. So if you do that effort, if you put another broadband in each one of them, or maybe even a very broadband, which is expensive, I know, you will gain fast information, and you will get, and those low frequencies will not be dispersed until they get to the station. You will record them. So the high frequencies will go away, but the low frequencies will be there and will be there fast.
So this is a study we did for Kelut, okay, full disclaimer, to my knowledge, is the first time we recorded a seismic signature of the eruptions 7,000 kilometers away. So we have the signal of Kelut eruption in New Zealand. That is not always the case. You need something that is extremely well coupled to the ground. So I agree with you, Itai. It's, if I have strongly coupled low frequency seismic waves, they will travel fast and far, but it's not always the case.
Okay.
And yes, if you couple infrasound and seismic, you gain in accuracy for the back azimuth. It's true because the very broadband instruments, if you concentrate on the horizontal components, will tend to tilt in the direction of your source.
Okay, thank you.
You look mildly happy, but if you want to follow up, you can shoot me an email.
I'm sure you are aware of the works of Matosa, of Robin Matosa.
Yeah. Those are usually nearby stations.
Okay. Yeah, true.
Yeah.
More questions, guys? All right. I think, Benoit, I think you're off the hook. I'd like to thank you once again for a great talk. I had a great time. And our last seminar for this semester will be next week. And then we'll take a break between the terms and come back online in the next term. All right. Thank you so much. And,
well, thanks everyone. Thanks Uri for the opportunities. Thanks Amot for the invitations, and thanks everyone for listening. And thanks Leo for showing up.
I'm here. It was great. Thank you so much.
Thanks everyone. Thanks Tay for the questions. And yeah, Robin Matosa is like up there. I'm following him closely, and I don't miss an opportunity to touch base with Robin. So it's an excellent point. They tend to concentrate the coupling within seismic and infrasound tend to be on the flank of the volcano, and he did a lot of work using the IMS data as well. So it's a good reading. Thanks everyone.
Thank you. Good day. Good night.
Bye.
Salut.
Salut.